It's my pleasure to introduce Dr. James Doyle. Jim is Senior Scientist for Mesoscale Meteorology in the Marine Meteorology Division of the Naval Research Laboratory. His research interests include non-hydrostatic models, predictability, tropical cyclones, coupled models, and topographically forced phenomena. Jim is a principal developer of the Navy's coupled ocean atmosphere mesoscale prediction system, a very important system used worldwide. He's participated in many field projects, T-REX, T-Park, DEEPWAVE, among others. Some of the awards he has received include the Top Navy Scientists and Engineers of the Year Award, the Arthur Bisson Prize for Naval Technology Achievement. He's been named a Fellow of the American Meteorological Society and, of course, the most coveted of all EOL affiliate scientists. Today he's going to tell us about results from the DEEPWAVE project. Jim.
Okay, thanks very much. Turn on my mic. So thanks very much for the introduction. I really appreciate the invitation to talk today and to be an affiliate scientist. It's a great opportunity to learn more about what's happening at NCAR, and I always appreciate coming to NCAR because I really feel like it's sort of the center of the universe from many perspectives. I know my wife grew up on Long Island, and she always told me New York City is really the center of the universe. I remember going to New York City, fairly recently for the first time, spending a number of days there, and I did feel like, hey, this kind of feels like the center of the universe. But that's what it feels like here in terms of meteorology, is like this is really so much happening, and I really appreciate everyone taking time out to meet with me this week and also come to the seminar. So anyways, this is a bit of a overview talk on some of the work we've been doing and our colleagues that have been involved with DEEPWAVE. And a few of the folks are listed that we've worked with below. And this includes the principals who have been on DEEPWAVE, and it was really spearheaded by Dave Fritz and Ron Smith, and also included Mike Taylor, Andreas Dornbrack, Mike Udstrom from New Zealand, and the entire DEEPWAVE team, of course. The sponsors of this were mainly, of course, NSF, but we also had sponsorship through the Navy as well, and there was some funding that went towards augmenting some of the flight facilities or the flight hours. So what is DEEPWAVE? So this is always in this day and age, if you ever want to find out what is something, you go right to your browser. And I remember when we first did this after DEEPWAVE, we were a bit disappointed because we thought, of course, the field program's going to come up, but there are apparently other meanings to DEEPWAVE than gravity waves. And you can see there is one DEEPWAVE related thing. For some reason, David Cameron came up. I'm not sure why, but then there's a lot of other kinds of DEEPWAVE. And so it's not... If you're here to hear about the other kind of DEEPWAVE, you're in the wrong place. So anyways, this is the outline. I'll begin with a little background, especially highlighting why we're doing this problem. Some highlights from DEEPWAVE, so I'll include lots of snippets from some of the studies carried out by the various PIs, and then talk a little bit about the aspects of the problem that we've been working on related to sheared flow. So the southern hemisphere has really strong jets. The lateral shear, the horizontal shear of these jets and the vertical shear could be very important. And then talk about predictability and then summary. So we spend most of our time worrying about the troposphere and maybe the lowest 1 kilometer if you're a boundary layer person, or certainly the lowest 10 kilometers. But this program was really focused on a more integrative sense to go from the near surface up to about 100 kilometers, which passes through tropopause, stratopause, and the mesopause as well. And so why are we so interested in these gravity waves that vertically propagate up into high altitudes? So when gravity waves propagate into high altitudes, they often break down into turbulence. And these turbulent regions can be really important in terms of the overall momentum budget of the atmosphere. And in fact, you could show these two profiles highlight that if you take out the wave drag from a global model, you'll get a zonal circulation that is in the actually wrong direction compared with actual observations. So in order to properly represent this breakdown process, gravity waves are really critical to get the right sign of the circulation in the mesosphere. So we're interested in, so there's that, it basically says what I just said. So here comes some cheap animation. So gravity waves can be excited, and waves can be trapped laterally. They can propagate vertically. And those are the ones we're interested in. They can break, and they can excite additional waves that propagate to high altitudes, and also can actually propagate down as well. And this, in an integrative sense of being able to measure gravity waves from the troposphere all the way up to about 100 kilometers with a set of new remote sensors on the G5 was really new. No one's ever tried that before, to be able to look at gravity waves over such a deep layer. And it really brought together two communities that would go to separate meetings, which is a bit strange, but you'd have the high altitude gravity wave people that went to their own meetings, that separate meetings from the lower troposphere or the troposphere lower stratosphere. So this really brought together those communities too. So DEEPWAVE initiative was really centered on New Zealand and focused on providing a new understanding of the gravity wave dynamics and their impacts. And this is just a cross-section showing the mean circulation going from the equator to 90 south. And these contours are the wind speed, meters per second. And a couple things to highlight, first of all, in the lower troposphere, around the mid-latitudes in the southern hemisphere, you have the mid-latitude jet. If you go further to the higher latitudes in the southern hemisphere, you can see this polar, what's sometimes called a polar night jet, a stratospheric jet that is very strong, averages 90 meters per second or so, up to 100 meters per second, around the 50-kilometer level. And then if you go further north, you have the polar vortex, and you get polar stratospheric clouds and other aspects. And so here comes another cheap animation. So this region is so interesting because the increase of winds with height to high altitudes allow waves in a very unique way to propagate to high altitude. And there's not that many places in the planet that this takes place consistently. So that's why we went all the way to New Zealand to look at this problem. So actually, if you use satellite data and look at high altitudes at 3 millibars, so that's up at fairly high altitudes, and look at the radiance perturbations, which are surrogates for gravity waves from some of the satellite instruments like AIRS, you find in the climatology during the winter months in the southern hemisphere a maximum over the southern Andes. So one of the first places we looked at to possibly have this program was in the southern Andes, but that wasn't quite so easy to carry out in that part of the planet. And you can see there's other areas that have maxima, including New Zealand is one of the really strong regions, and also Tasmania too. So New Zealand was a perfectly good place to be able to study these, and you can just see, highlight from the climatology, you see maxima over New Zealand, a nice max over Tasmania. So the field campaign took place in June through July of 2014. It was, as I mentioned, Dave Fritz here on the G5, Ron Smith were the two PIs from the NSF side, and lots of folks from EOL were involved, and a number of you in this room actually were in New Zealand that actually contributed, and it was a really great field program, I think. It was taxing. We had all of our flights at night. There were a lot of flights. I think we had 26 flights. I'll talk more about that, but it was a really great team effort. I think we actually needed every single person that was involved to be able to carry it out successfully. And we had a number of graduate students who worked extremely hard, including Chris, who's here in the audience, that without, like most of these programs, without the graduate students, I think almost all the programs would probably fail. So there's sort of like the backbone of a lot of work was done by some of those students. So the field campaign, of course, included this LiDARs that were with the ports oriented out of the top of the aircraft. There's 3 LiDARs. I'll say more about that in a minute. And we had also the DLR Falcon with their wind LiDAR that flew for part of the field program. So we had some coordinated missions with them. This just highlights a little bit about the geography for those of you not familiar. We're based in Christchurch, and we had some nominal flight plans that would go upstream of New Zealand. We had some plans to go over Tasmania and over the southern islands, and this was sort of put together ahead of time. Oh, that's just a photo from inside the cabin that shows 2 of the LiDARs oriented in the back of the cabin. There's our ops center in Christchurch. That's where the aircrafts were based. We had the wind profilers. Bill Brown and his team were in Hokitika on the upstream side with the ISS, and in Haast a little further south, the NIWA team had some radiosondes launched, and then the Germans, the DLR group was in Lauder launching radiosondes with a ground-based LiDAR, and there's an IR mapper, and those are sort of some key ground-based instruments. And additionally, we had some extra soundings that were taken in Hobart and also Macquarie Island too. So those were all important parts of the program. So this is sort of a look at the 26 flights, and it looks like we covered things pretty well. We had a number of them upstream, most of them over the island measuring the orographic waves. We also had some measuring non-orographic waves to the south, and it was really a good mix. It was dictated basically by the weather, and I think everybody was pretty happy with the data sets. This just shows the instruments, the existing instruments, the in situ dropsondes, the MTP were on the aircraft, and the new instruments, the Rayleigh LiDAR and the sodium resonance LiDAR. These were from Dave Fritz's team. And then this MTM, or the AMTM, the Advanced Mesospheric Temperature Mapper, which got measurements up to 87 kilometers, came from Mike Taylor and his team. So these LiDARs measured temperature and some backscatter at various levels in the atmosphere, so that we had almost a continuous group of measurements from the aircraft up to 100 kilometers. So that just shows the different levels of these LiDARs. First of all, we have the dropsondes, MTP, the Rayleigh LiDAR, up to about 60 kilometers, and then this the sodium LiDAR from Dave's team between 80 and 100, and the airglow imager up around 86 kilometers. So this airglow imager is an interesting one because it's taking advantage of a chemical reaction that takes place in the high altitude. So what you're seeing is from a NASA satellite that is showing the airglow and the aurora in the southern hemisphere. And this airglow layer occurs because of OH chemical reaction that is emitted then in the 85 to 90 kilometer range. And the line strength of this is temperature dependent. And so this AMTM is then able to take measurements, provide measurements of temperature perturbations, which we expect from to be correlated with the gravity waves. So some highlights from DEEPWAVE. So first of all, this is a comparison of the Hokitika wind profiler U-wind component, and these are the different IOPs. So there is a total of 16 IOPs. You could get a sense of the warm colors here, stronger winds, stronger cross-mountain winds across the New Zealand Southern Alps. You can see almost all these IOPs have relatively strong periods of cross-mountain winds during the program. We had a cluster of IOPs early, in the middle, and then later too. And some of these not all of them were over the island. So if you look at the higher altitudes in a climatological sense, this is from the ECMWF model now. So we're looking at 0 to 80 kilometers in their model. And you can see also a fair bit of variability in the winds and potential temperature and contours, so the wind speed and color. And it varied quite a bit between over 100 meters a second at times in the mid-stratosphere to in the 60s. So there's a lot of variability. Some of this, at least, is because of the gravity wave nature. So the background winds are really important for how the waves propagate. And that's one of the things that we learned from this. We knew that would be the case going into it, but I think it gave us a new sense of appreciation. So so a few highlights. This is from some work that Ron Smith and his team led, and there was a particular day we're flying across the New Zealand Alps, Southern Alps, and what's shown here is the vertical velocity, 2 different altitudes, in black 12 kilometers, in red around 14 kilometers, and then the U wind component. And you can see the vertical velocity sort of at low levels, lots of wave structure that much of it was non-steady waves that were downstream of the mountains, and passes back and forth. Oftentimes these waves wouldn't line up, so they weren't exactly steady trapped waves. There were some sort of nonlinear waves. This particular leg went up about 2 kilometers, and you could see signatures of lots of high frequency in the vertical velocity and turbulence. Peak vertical velocity was a couple meters a second, but you could see the U wind component drops down to 0 or just below 0, which both are signatures of wave breaking. So the wave is actually overturning and turning into turbulence at this point. And this is the terrain beneath. So this is happening sort of right over some of the highest peaks of the Southern Alps. So we had several mountain wave breaking events that were observed. They're very hard to predict and know that you're going to encounter these, but I think there's very valuable data. I think to date, we have high rate data from this, but I'm not sure anybody's really looked at in terms of publishing an article about the turbulent characteristics of these events, but I think it's still an open question. Oh, there's nice circles that popped up. So also Ron and his team have been looking at momentum fluxes, which is a very important quantity for our model. And I think one of the interesting things that popped out of this is, this shows the number of the research flight number, and this shows the zonal momentum flux on this axis. So the zonal momentum flux is negative, showing that it's a drag on the atmosphere for all of these. And you can see that a lot, each one of these dots is a momentum flux calculation along the legs that cross the mountain. So there's multiple legs that were repeated back and forth. And you can see some of these all pretty much agree. Other cases have lots of variability. And that's still sort of one of the open questions. There's a number of suspects of why that is. One of them could be non-steady conditions in the upstream. It could have to do with nonlinearities and non-stationarities. So there's different reasons. But I think comparing to some of the other field programs that we've had, like T-Rex, this was something that stood out a bit more in terms of the variability of the momentum flux crossing the mountains over a several hour period. Ron and his team also were able to compute the momentum or the energy flux and compare that with the energy flux derived from the momentum flux using the Elias and Palm relationship. You'd expect a 1-to-1 relation between these two. This is sort of a fundamental relationship in terms of gravity wave theory, and the accuracy of the measurements and the differential GPS are really important, and they show that pretty good agreement between the two. And I think that was a really nice confirmation, and it was done to a higher degree than we've ever been able to do before with these sort of measurements. And so that was, I think, really satisfying, especially considering the Elias and Palm relationship has a number of assumptions built into it, and it still holds, which is, I think, encouraging, saying that our theories are on pretty solid ground. So Chris, who's in the audience, Chris Cruzy, had a number of studies that have popped up out of DEEPWAVE as part of his thesis, and he had a bunch of publications that have appeared in the literature. A lot of it has to do with the gravity waves and gravity wave drag, one of the aspects of the DEEPWAVE program that we didn't really anticipate, I'll call it a discovery coming out of DEEPWAVE, was Chris and Ron came across a number of cases where the gravity waves didn't necessarily propagate to high altitudes. They were frequently attenuated during in periods of weak winds in the lower stratosphere, usually somewhere between 15 and 25 kilometers, and they called this a valve layer. And so this valve layer really is controlling the gravity waves and their properties and their ability to propagate through this, which essentially controls the momentum flux. So it's the analogy that Chris had is in terms of, it's like controlling the mass flux through a pipe. So this is, I think, a really nice contribution in terms of our gravity wave understanding. And this shows the average winds. And you can see the variability that you start to see between 15 and 25 kilometers throughout the period. The momentum flux varies greatly. You could see, to some degree, nothing above 15 to 25 kilometers at times. And then you see there are periods where it propagates, the waves are propagating deeply. Momentum flux is all the way up to 35 kilometers, and you can see the zonal gravity wave drag computed based on that. These are model results, but they've been verified in terms of the properties of the wind velocity with some of the observations. So I think it's a nice study that has explained why we see so much variability in the upper stratosphere all the way up through the mesosphere. So another interesting study that came out of DEEPWAVE was wave propagation from small islands. And we had some notion that some of these small islands may be contributing to the overall momentum budget and may be important in terms of their properties. This is air's brightness temperature. You can see the big maxima over these islands, and then you can see a little maxima over this island called Auckland Island, and not really any signature from this one called Macquarie. So there is some pretty strong flow across these two islands, so we thought would take advantage of the G5's range, fly south, and fly some legs over Auckland, and then fly further south over Macquarie. So it was a great demonstration of the importance of the G5 range. And the cool thing about these islands is that these islands are often not even represented in global climate or global circulation models. So they're kind of small, and let's ignore them. There are investigators that have reported improvements in these global circulation models in terms of their cold biases when you start to add in extra sources of wave drag. And so the question is, where is this extra wave drag coming from? And so the DEEPWAVE went out. One of the objectives was to be able to go out and measure wave characteristics over these islands. And you can see I mentioned this little maxima over Auckland. So a little bit about geography, the geography of Auckland Island and Macquarie. So Auckland Island is an archipelago. It's complex topography. Its peak topography is around 700 meters. Interesting, it's been the site of many shipwrecks. There's amongst the folks that have been marooned there include this Captain Thomas Musgrave. He was marooned in 1864 for 19 months, but he logged daily temperature, barometer, and wind speed obs during that period. So he sort of forged ahead as he struggled to survive on the island, but still managed to take observations. That shows a lot of commitment. So Macquarie is a part of Tasmania. It's a World Heritage Site. It's home to the entire royal penguin population, and they come back every year to nest there. It's really impressive. It's apparently the only place that they nest in the entire planet. So it's a very remote part of the planet. I'll come back to that in a second. So the dropsondes upstream of those islands indicated winds of about 20 meters per second impinging on those islands. So the topography is not very big. It's not the type of things that we would expect to excite big waves. So here's the AMTM, the temperature mapper that's looking at that 86 or 87 kilometer level, the overhead camera here, the side cameras that are shooting out the side of the aircraft, and you could begin to see the wave structure that was present downstream of Auckland. So that's pretty interesting, and we could see lots of non-steadiness. The aircraft went down over Macquarie's, coming back, and you'll see the wave structure again as it passes over the island. Right here, you start to see these arcing waves at 87 kilometers, which is really remarkable. And it shows that these waves are vertically propagating, and we're sort of making these detailed measurements for the first time that these little islands are launching these wave packets going to high altitudes. So the AMTM, you could convert some of this to temperature perturbations. Mike Taylor and his group did this, and you could see some of these nice temperature signatures, fairly big in terms of the range of the temperature. These are larger amplitude waves, and they're really perturbing the upper levels. There's also some sense that the different legs that were flown, that there's non-steadiness, and maybe the waves broke and dissipated. That's one of the hypotheses. So we used our Navy's model called COAMPS, and we've simulated it with fairly high resolution and model top around 60 kilometers, and we were able to kind of capture some of the asymmetries of these arcing waves downstream of Auckland, up to 45 kilometers in this case. There's a little tiny island called Campbell Island that has a peak around 500 meters, and you can see a little signature there, but it sort of gets attenuated or dissipated higher up. And so it's not quite big enough to have a strong signature. So back to Macquarie, which was this really remote island south of Auckland, and it's actually a radiosonde location. So there's folks that are stationed there year-round, and we had contact with them. We would email them that, hey, we've got this interesting IOP coming up. Can you launch instead of twice daily, how about 4 times daily? So they were more than happy to work with us. They were very excited about it. So you could imagine that there's not a lot of things happening down there. There's not a lot of activity. They were so charged up that it was probably one of the few clear nights they had, and they went out and they took a time exposure of the G5 passing overhead, and you can see the lights from the G5 as it went by. And so they said that they just don't see very many aircraft. And this is from the officer in charge who said, Keon Stevenson, it's quite rare to have an aircraft fly over Macquarie Island. Life on the island consists of 15 wintering expeditioners. At this stage, our trips down here looks like 13 months with current shipping schedule, so they arrive by ship. We have 9 months to go. A winter for the personnel is a true test. So this is pretty rough conditions. I think the day we flew over it, they were gusting to 61 kilometers per hour at the surface, and temperatures, it rains almost all the time, and temperature 5.5 degrees Celsius, so it's not great conditions. So Macquarie also showed some nice arcing gravity wave signatures, and it was a lot of asymmetries, not quite as much to the south, more to the north. And this was really neat to see because the island tops are around 500 meters or so. It's a really narrow little island, and I don't think we had the impression that waves could reach this altitude before. We did some simulations with a 500 meter resolution or 550 meter resolution, and you could see the model was able to capture some of the wave signatures propagating downstream, so that was really good to see. So we're working on a manuscript on that. So one of the whole objectives of DEEPWAVE was to be able to link the lower tropospheric and lower stratospheric waves all the way up to the mesosphere. And this is one of the examples from DEEPWAVE that appeared in Dave Fritz's overview paper. So it shows, this is from the Rayleigh LiDAR, temperature perturbations in color, and then ECMWF temperature just for comparison in these black contours. And you can see this nice wave structure with the gravity wave that's being launched in the lower part of the atmosphere, propagating up through the lower to mid stratosphere. The sodium density calculations or the sodium density observations showing some steepening of the waves as they approach higher altitudes. So this really shows a nice link of the progression of these waves. Now, these waves that are shown here are rather long in wavelength. These are distance that goes east to west. Every 100 kilometers is along this axis. And so those are considered fairly long gravity wavelengths of around 200 kilometers in the stratosphere. And then smaller waves in the upper stratosphere in the up to the mesosphere. And so one of the things that was apparent coming out of DEEPWAVE that we knew about, but we were sort of wrestling with of how to interpret some of these cases, is that these long waves, if you look at the propagation time, may take more than 24 hours to propagate up to these higher altitudes, which is a long time for these waves to go up. At the same time, the waves that I showed earlier that were launched by these tiny islands have really fast intrinsic frequencies. So those can propagate really quickly up to high altitudes. So you have these short waves that can propagate in half an hour to a couple hours. And so some of these measurements that show multiple wavelengths may be a mixture of yesterday's sort of leftovers and today's waves. And this is a little bit hard to tease out. And so I think that's one of the challenges that still remains, is piecing together the story about all of these wave sources. So Katrina Bossard, who's works in Dave Fritz's group over at, she was at GATS. I think she's still there. And no, she's in Alaska now. Okay. But she's done a number of nice papers that has to do with coming out of DEEPWAVE as part of her thesis. And she was one of the folks that flew a number of missions helping with the LiDAR. And this just shows one of her papers that came out last year in JGR, the sodium density perturbations. You can see lots of high frequency structures. So we start to see these horizontal scales here that are a bit longer, and then these very short scales. And there's some evidence that these may be waves that are emitted, like I talked about early on, that are emitted from these braking regions. So these are secondary gravity waves that are propagating vertically. And these wavelengths indicate also that there may be a nonlinear generation mechanism. So this is one of the objectives that we had scientifically coming into DEEPWAVE, was to be able to hopefully observe some secondary gravity wave events. And this is one of them that she and her team has highlighted. A little bit about more from this AMTM. This shows a couple of different cases that we noted. This was a strong propagating case, and you can see there's some nice wave fronts that are more or less parallel to the orography in New Zealand. There's a couple in the northern part of the southern island. And then if we look on a case that we had rather weak forcing, we actually see some wave crests that are more or less perpendicular to the peak, the terrain ridge, and sort of streaming downstream. And that's an aspect that I'd like to talk more about in a moment. Finally, we had a number of cases towards the end of the program where there wasn't as strong a flow across the terrain. And this was a great opportunity to go further south, around 60 south, and be able to try to observe non-orographic gravity waves. So these are coming out of jet streams. And this is a great case where we have nice measurements from the Rayleigh LiDAR that show these temperature perturbations, these structures that are propagating in the vertical that are being emitted from these cyclones in the southern hemisphere. We don't parameterize these in our models very well, and that remains one of the big unknowns. So that's some of the important data that was taken out of DEEPWAVE. They're really rare observations of non-orographic gravity waves, particularly to this altitude. So sheared flow. So there is a number of events that I mentioned where we saw these waves trailing downstream. You could see it in the climatology coming off of the southern Andes, where they trailed far downstream. And some of that is non-orographic, but some of it is orographic. This is one case, Research Flight 4, where we had a nice transects, and we had these waves propagating downstream. There's RF22, which also showed these more or less perpendicular to the ridge. These are high altitudes, up around 2 millibars. Nevertheless, still, we wanted to better understand what was going on. So to better understand what is behind this, you look at the upper level winds. Like I talked earlier, we have this really strong jet in the stratosphere with really strong horizontal gradients along the edge of the jet. So just to orient you, here's South America, here's New Zealand, and you can see the southern island sits right along the gradient of this. So it's really strong horizontal lateral shear. This just shows some model simulations of these arcing waves that were basically able to capture the characteristics of these that we observed in DEEPWAVE. A little bit about the details of some of the dynamics. Now, this is a wave spectrum, the horizontal wave K and L on each axis. These are two circles show wavelengths of 200 kilometers and 100 kilometers out here. And if we look in this particular case, we had winds at mountaintop that were southwesterly, so it was a bit of an unusual case, so not so much cross mountain. In this particular type of flow, we had higher up, the winds were westerly. So we have intrinsic frequencies in terms of the wave propagation that result in filtering of the gravity waves. So because of this change in direction with altitude, some of the wave numbers in that spectrum get filtered. And so only part of the wave spectrum is emitted to higher altitudes. Additionally, we have waves that are filtered by something called a Jones critical level. So in other words, the wavelengths are long enough so those really long waves aren't permitted to propagate also. So we only have part of the wave spectrum making it to high altitudes. We can look at this in a ray tracing form. So this is using linear theory, and you launch basically waves from a source, like from orography, and watch what happens to them. So if we first look at this lower panel, this is in a YZ plane. These are different wavelengths that show these longer wavelengths never really make it up to the high altitudes, where the shorter wavelengths do. So they're able to propagate vertically. And then if we look at the ray paths now for waves with a specific set of wave vector angles, so we look at waves between 140 to 270 degrees, we see that there's only certain parts of the spectrum in terms of the direction make it to high altitudes. That has to do with this filtering. So it's actually a very specific part of the wave spectrum is getting up to high altitudes. And so we've looked at this in a very simplified, idealized framework where we have a strong jet stream, and we are able to represent the lateral shear. This is a cross-section, vertical cross-section. And then this is a plan view, and we put in a mountain with a 1 kilometer high top, kind of emulating what a little island might see. And we can see at 10 kilometers, we have a nice parabolic shaped gravity wave that we expect from our theory, and we're able to have confirmed that through a lot of different field programs. And as we go to higher altitudes, up to 25 kilometers, you could start to see these wave fronts are swept downstream more or less because you have really strong zonal flow, so strong from left to right, and they're really normal to the wave vectors, and the energy is getting swept downstream, so you end up with this big asymmetry in the wave characteristics. So this is sort of the idealized version of these trailing waves. So the interesting thing about this is that the trailing waves actually don't carry much momentum flux. So the other waves, they're fairly long in wavelength, but if you do look at the momentum flux, this is the jet core, and you find that below 10 kilometers, the momentum flux is really strong, so it's a big drag in the troposphere, lower stratosphere. Above that, you actually see the momentum flux tilt back into the jet associated with this wave refraction. So the waves are actually being refracted by the jet itself. And we can see, we can put a idealized or real topography from New Zealand into this jet, and we could see the same type of arcing signatures that we see from the satellite data as well. These vertical velocity perturbations are small enough that we can't really measure them with the G5, even though we had some missions trying to, but they're small enough perturbations at the altitude of the aircraft that it's difficult to measure. So we could see them in the remote sensors, but not as well in the in situ data. So the last little bit is about sensitivity and predictability. So we had a couple of missions devoted to better understand what controls the model's ability to predict these sorts of events. And this just shows this particular case I talked about earlier that Ron Smith and Chris and their collaborators looked at, and it was a wave-breaking event, a fairly strong gravity wave event. And so we have a modeling system that's called an Adjoint that's able to actually compute what impacts the waves that are launched for this particular case. So I thought this was supposed to be animating, but I think it's just very slow. Okay. I think it's some Microsoft glitch where I have to keep the mouse moving for it to animate, which is really strange. So let me go back. So it's actually fairly convenient. So in this particular type of model called an adjoint, it actually, the notion of it integrates backwards in time. So you ask a question, what impacts the 36-hour forecast? We're looking at the 36-hour forecast winds over the terrain of New Zealand, and we integrate that backwards in time to find where the initial state is most sensitive. So let me let that propagate further back in time, back to 0 hours. So you can see these height contours in black actually moved upstream, so things are moving backwards. And we find that at the initial time, this region is the region of highest sensitivity. So the idea is if you can take observations in this region, improve the initial state, you should improve the cross-mountain winds in this region, which should improve the gravity waves. So this is sort of a chain of, in terms of predictability and better understanding how that works. This just shows where those sensitive regions are. And we flew 3 missions, and we found almost always these sensitive regions corresponded to strong troughs and strong synoptic scale features. So let me just go a bit further and show these 2 different missions highlighting that we flew. This just basically shows the G5 tracks and their drops from these 2. You can see 2 different cloud shield systems that were associated with this. These are the 250 millibar winds. They had really strong winds in the Tasman Sea. The sensitivities are shown here. So we dropped these SONs in these regions and dropped SONs outside the sensitive regions. We could show that if you put in perturbations into these regions, you get big changes in the velocities 24 hours later of 8 and 14 meters a second. So it has a big impact on the forcing as the flow crosses the mountains. And then we flew missions the following day that were focused on measuring the gravity waves. So we called these the verification missions. So we were able to take observations 24 hours prior to the mission and then see how they affect the gravity waves the next day. So some of this work is still ongoing, but we're able to quantify using some of the technology we have to look at the impact of these dropsons. And so one way of looking at it is in terms of a total impact. And we find that these dropsons had the 4th most impact of any observing system. There is AMDAR observations from aircraft, commercial aircraft, satellite winds, radiosons, and dropsons was the 4th. But if you look at it on a per observation basis, the dropsons actually were the most important observation in terms of what affected the forecast in this region.
Was that because they were done in the target area as opposed to doing in a randomly scattered?
I would like to think so, but I don't think we fully answered that question yet. Yeah. We did look at a number of cases like this example. using a four-dimensional variational assimilation system. We did some data denials, taking the drops out completely, putting them in, and we get perturbations like this in terms of the differences in the 6-hour forecast right over the southern islands of plus or minus 10 meters a second, which is big. So those sorts of details could potentially be important. And it shows maybe some of the subtleties that are going on in terms of how the waves are launched and maybe some of this variability that we're seeing in terms of the momentum fluxes that were in some of the previous studies. So let me just summarize. So I think the DeepWave field program was really successful. It carried out 26 G5 flights. There was a number of Falcon missions, sampled all sorts of different gravity waves, mountain waves, non-orographic waves. We were able to look at the sensitive regions for the first time and better understand how waves are being launched. They're being launched really by these baroclinic waves that come every 2 or 3 days in the southern hemisphere, and pulses of strong zonal flow that launch these waves. These measurements included this really unique, comprehensive suite of ground-based measurements. We had the ISS on the upstream side and radiosondes, LIDARs, ground-based LIDARs, IR mappers. I think the key results was, I think, taking away, we had no flights where we didn't measure interesting waves. I think even the cases with some of the weakest flow actually had some of the more interesting more interesting gravity waves. So there was really a rich spectrum up to 100 kilometers, extensive large and small wavelengths, there's challenges with that in terms of interpretation, strong evidence of deep propagation in a number of cases, and then the predictability links that we're trying to establish between what's going on in the low levels and the upper levels are, I think, quite interesting. So, some of the remaining mysteries that I think are still outstanding, there's these sort of rapid changes in the fluxes I talked about, how these waves are getting launched, the role of the boundary layer. The weak gravity wave cases really had the best deep propagation events, which is a bit counterintuitive, but that was, I think, an interesting discovery. Non-orographic sources have been looked at a lot less. I think they're less clear on what's going on with that, and there's probably this data set will still be mined in the future for years to come. We still have some predictability issues to wrestle with. So I think overall, the PIs were very happy with the program. Everybody really appreciates all the hard work from the EOL team and the NCAR team and helping make it a success. So I'll stop there and happy to address any questions.
Questions for Jim?
So is there going to be a deep wave too?
That's a good question. I think at one point there was a proposal for using some of these instruments to look at the open ocean waves, and I don't think that was successful. And I know Dave Fritz is in the process of proposing a possibility of using these instruments to look at gravity waves launched by hurricanes. So that may be not exactly a deep wave too, but I think an opportunity to better understand how some of these other sources are contributing to the gravity wave spectrum and momentum fluxes.
Okay. Do you have a guess as to why the weak gravity wave cases or the weak forcing cases had the best deep propagation? Is it amplitude or wind profile or?
Yeah, that's a great question. I think intuitively, in a hand-waving sense, we had thought that maybe the stronger cases with the bigger amplitudes actually ended up breaking and going through some breakdown process and not making it cleanly to high altitudes, where the little waves are the ones that were able to go to higher altitudes. And if we had probably better appreciated this ahead of time, we might have tried a few more cases of these weak wave events just to see if this is really true, and I would get a bit better sample. But I think it was interesting. There's a shorter flight, I forget which research flight, that had some really compelling observations from that one. That's, I think, Steve Eckerman led. Yeah.
So do those weak waves tend to be also the shorter wavelength?
Yeah, that's a good question. I don't know offhand. I'm not really sure. Yeah, I think it may have varied, but I don't know if how many observations we had of those. Yeah, it's a good question.
Other questions? Yes.
So, not knowing a whole lot about it, is it easier to have a critical layer when you have low wind speeds than high wind speeds?
Yes, yeah. So the critical layer occurs if, for example, you have winds approaching zero at an altitude above the surface, above the mountaintop. That's one way. Or you can have these directional critical levels where essentially only part of the waves get filtered. So both of them are filtering processes. Sometimes if you have this zero wind layer, this critical level in the mean state, that could be a pretty strong filter on the waves themselves. They get really short vertical wavelengths and end up breaking down into turbulence and never propagating above that. So that's one of the reasons why in the northern hemisphere we typically don't have that really strong polar jet. You have sort of a critical level, like during T-Rex, we thought we had probably a critical level around 20 or 25 kilometers, and waves just never make it up to the high altitudes. So that's why the southern hemisphere is so unique. It's the critical levels that filter in the northern hemisphere more.
Other questions? Yes.
This is a tough one. What kind of measurement systems do you wish you'd had been able to take, or what kind of measurements would you like more of?
Right, good question. Well, for one thing, you won't like this one, but this comes as New Zealand is a small island. It would have been great to have more measurements upstream, so to have like a floating profiler offshore. I mean, to have the sort of measurements that were not impacted by the terrain themselves, because the ISS was as far west as we could get without being in the water, but at the same time was still impacted by the terrain. So, probably having some upstream measurements more may have been interesting. I guess if we had the ability to tease it for our own personal research at NRL, maybe teasing out a bit more of these gravity waves that are these trailing waves that had rather small perturbations. It was really hard to tease out any signal, and we may be at the signal to noise ratio for some of that. And that was a bit surprising to me that we weren't seeing stronger signatures from those waves. We expected a bigger amplitude to be able to see that. So, but there's probably a longer wish list from Chris, maybe. I don't know, Chris, do you have any, to put you on the spot, do you have any wish lists of things?
No, I don't even know if it's possible, but some really powerful profiling LiDARs that
Yeah.
can give you profiles of wind speed that are kind of continuous in time and space, that go through at least the tropopause, but the higher the better.
For winds and temperature?
Yeah,
All of the
everything.
above.
I mean, but
Right,
you take what you get.
right.
I'm puzzled, too, by your comment about not being able to tease out the weaker contributions in some parts, because the wind system was really good.
Right.
It was the best that I've ever seen it perform. And we've also worked on it some since then. So it might be worth a little bit more work with the post-project processing to see if we can do better than that. For example, there is a Kalman filter approach that can be applied which will remove a lot of the things that might be noise in there. So I wonder if that's worth some more, because that's about as good as we can do, I think, in the winds.
Yeah, and there's one other part of that I didn't mention that I should have, is they're really exceptionally long wavelengths too. So you have the small perturbations and really long wavelengths, and some of our legs may not have been long enough in some cases to even capture, full wavelengths. It's their offshore, sort of downstream. But we do have some that we attempted to do this, so it may be worth talking more with you and others about maybe how better to tease that out.
And that is the kind of thing that the improvements would help on, is the longer wavelengths. It's easy to get the short wavelengths, but to get things consistent over a long distance and avoid a gradual drift in the offset that contaminates, that is a problem. So I think that's worth some more look.
Okay, great. Yeah, thanks for that comment.
Other questions? Okay, let's thank Jim again.
Thanks very much.